So I'd mentioned before that virtualization allows you and gives you the ability to take a container and effectively wrap it around the application. Well, what they're doing with that is they're going from this one application for a compute node model to wrapping containers around it and multiplexing applications onto a compute node. So if you can go from one application per compute node and 15% utilization to 10 applications per compute node, you not only get rid of 9 compute nodes in the infrastructure that supports it and the space requirements around that, but you get the server utilization gets driven significantly higher than 15%. And so that's going on in very dramatic fashion in many, many customers today. And there are implications in the data center for that. The servers tend to be higher performance and higher power. They are getting more efficient, but it tends to create cooling and power hotspots within the data center. It requires faster networking connections to make that work, so higher performance networking components mean more power in the data center. And it drives the complexity up somewhat inside of the data center as well. This was a couple of key points that I picked out of a customer survey that we've run, I think in July of this year. It's around 900 data center customers. I think John will correct me if that number is wrong. But the response from them was that greater than 50% of the production applications that they were today running in that one app per compute mode model was that more than 50% of their applications over the next year were going to be hosted in virtual containers. And that virtualization technology was the key driver for changing out the IT infrastructure over the next year. And so we're doing a lot to build network infrastructure, compute infrastructure, storage infrastructure in direct response to this virtualization. And as data center designers, we should be thinking about the implications of all the virtual machines and the fungibility that adds into those the data centers and the implications that has downstream. And then we also tested this premise of people's data centers expanding and having the same sort of requirements over the wide area that they host in the local area. And there was a resounding endorsement of that concept. And so we're busy, hardening other components of the network and adding energy efficiency into other components of the network as well in response to that. Where we're going to want to go in a long term, of course, is the idea of these fully virtualized data centers. Where virtual machines, people pick up the applications and they move them. So some of our customers actually pick up an application and move it to a different data center simply because the power costs less or the cooling costs less. And in other times of the year, they move it back to the original data center. So we're continuing to work on the mobility of these virtual machines. Over the next couple of years, the virtual machines will actually be able to move very, very seamlessly between data centers. So you'll see more movement of the data and more movement of the applications. And in the networking components and the storage components and compute components inside of the data center, the objective is to be able to control them with software, to be able to pick them up in pieces, a piece of compute node, a piece of networking, a piece of storage, an application load, put those together into effectively a little virtual data center within the physical facility, use those until the application load goes away, and then return those resources into the pool. And so this phenomena of data center infrastructure flexing up and down very, very rapidly and very dynamically is going to continue within the data centers, and it's going to get, I would say better, but for physical plant designers, maybe worse, over the next couple of years, and it's something that we have to keep in mind. If you think about the general trends, within these, this is a good way to summarize it, right? Applications are going from discrete to being as virtual workloads, which brings mobility. And we like to say that virtual machines are the new atomic unit of work within the data center. So everything is being built around the movement of applications and virtual machines. Servers, because they're hosting more applications, if you actually look at the data center trends and look at what people are buying for servers, they're buying larger, higher density servers. So more sockets, more CPUs, more heat, more memory, more cores in those, denser compute platforms. Fewer of them, but higher density systems being deployed in data centers. The networking technology is going to look a lot faster. Fortunately, we're making it much more energy efficient than it was even a decade ago. It looks much more like a bus. It's much higher speed. To give you an example, Brocade in this year, I think in November, will actually launch this product portfolio formally. It's a technology called VCS. It allows us to build very large, flat Ethernet mesh networks within the data centers, capable of running storage traffic, Ethernet traffic, data traffic, everything. And to just give you an idea of the size of that, we're able to construct a flat network with line rate, about 1,000 ports of 10 gig Ethernet in a very small space, and support 10,000 applications in really just a couple of racks within that infrastructure, and to be able to take those applications within that 10,000 VM sphere and move those at will. So the data center manager can literally pick up an application, move it to a compute node, and not tell anybody in facilities, not tell anybody in the compute farm, not tell anybody in the networking space. And there are similar technologies being rolled out from other players in the industry, but this is the trend, to build these large flat surface areas that give us the capability to move things around. Networking capacity, storage is also becoming faster, more agile. One of the things that's interesting in the storage industry is the storage players are now moving data sets around between arrays. So you can have an application that's very, very active, and the data will be sitting on an array, and they'll silently migrate that data to a faster array on the other side of the data center. And when the application calms down, it may take that same data set, may go back and migrate to a slower array or something with less performance. And so again, it's really on this theme of the resources in the data center are going to become much more mobile. The loads are going to move much more dramatically, and they're going to move really over distance and everywhere in the data center. So we have to accommodate that in the design. Now, over the last year, we've been, as Mike said, moving into this campus. So I want to take just a couple of minutes and talk about that transition and give you some of the facts and the figures and the lessons learned that we've had in this move. And I know many of you are going to go tour the data center facilities and the lab facilities that are here. So you'll see a lot of this technology in action. As Mike said, we eat our own dog food. Here, we build our own network infrastructure on many of the principles that we've talked about. To just set a little baseline here, again, as Mike said, we were located in 5 development sites around the San Jose area. Actually 5 data centers, not 3, as Mike said, across those sites. About 80,000 square feet in the labs there, and in the engineering spaces, about 7,000 of that in IT, roughly 2,000 racks of equipment, and 44 racks in IT. And as Mike said, very severe space, power, and cooling constraints. We were making decisions about where to put projects based on where we had parking lot space to fit the cooling trailer that Mike talked about, so we could actually put equipment into buildings. And that's just backwards, right? I mean, you shouldn't be in that situation, but that's the situation that we found ourselves in really over a decade. Today we're in 1 development site. We're in 3 buildings within this campus. It's about 560,000 square feet here. We have 1 data center for both engineering support and for the IT. Building 1, which you'll see down here as you walk down past the parking garage, is a full data center facility from bottom to top. Engineering really owns the top 3 floors of the data center. So 70,000 square feet of that is dedicated to labs. The IT facilities, even though we've consolidated them all, have come down to about 5,000 square feet. And there's actually a fair amount of room to still grow within that physical facility. I think we're only at about 60% rack load within that facility. And we've really done a lot in there to make sure that we are pushing the envelope in terms of a high efficiency power and cooling systems within that data center. One of the things that we've done in the network architecture in there is I was talking before about these flatter, faster networks. So typically you build networks in hierarchies. You build core networks and distribution networks and aggregation networks and access layer networks, and they're all wired together into this giant tree. In this particular IT facility that you'll see, we've taken roughly 2,600 server connections in there, and we've collapsed those into 2 routing chassis. There is no other network infrastructure in there. We've taken the entire network infrastructure that used to take power and used to generate a ton of heat, and we've collapsed that into 2 chassis. And in terms of virtualization, we're running about 70% of our production applications over there in virtual machines today. Combination of Hyper-V, of VMware, of Xen, Solaris logical partitions, things like that. But we're about 70% virtualized. Now, there's some applications that you're not going to get there on, some of the very high-end database applications that you may not see that, but 70% is a pretty good ratio. And you'll see what the consolidation looks like when you go over there. You'll be amazed that there are 2,600 server connections sitting in that facility that's over there. Prior to the move, the buildings, we had no LEED certified buildings within the San Jose area. On paper at least, we're meeting our Title 24 requirements, and we ran a PUE greater than 2. I won't tell you how much greater than 2, but certainly greater than 2. And we weren't really focusing on targeting energy efficiency. I mean, we were trying to grow the business and develop gear and get it out quickly, but we weren't really focusing on the energy efficiency. We didn't really do that very, very progressively until we moved over to this campus. This campus is a full LEED certified campus. We carry a silver LEED certification on the entire campus, on the buildings, on the shells. We carry actually a gold certification on the interiors and interior spaces within the building. We're about 16% beyond our Title 24 requirements, and our calculated PUE in the data center today is about 1.3, maybe a little bit better than that, but right now we're saying it's about 1.3. And we've done a ton of things that you'll see as you go through the data center and that I'll talk about to help try and drive efficiencies in there. High efficiency cooling towers up on the roof. And as Casey said, without moving a data center to Canada or to Washington State or someplace where the weather is very, very favorable, even in this area, we've got about a 2,000-ton waterside economizer that we put on the roof. So there's 3 900-ton chillers in the plant, and we're able to shut down 2 of those 3 chillers in the evening when the temperature goes down and use that waterside economizer to get effectively 2,000 tons of free cooling that we pipe into the data center efficiency, or into the data center facility. Electrical distribution, pretty pedestrian in the old buildings prior to the transmission. We did run primary and secondary leads into all the buildings to maintain uptime or resiliency into the lab spaces. Very limited use of high efficiency motors, high efficiency fans, variable frequency drives, things like that was over there. And very limited energy monitoring. The energy monitoring was really limited to looking at the consumption at the panels. There weren't active energy monitoring systems actually put into the data center. After the transition, again, we have A and B side power that feeds into the campus buildings, but one of the things that we've done and one of the reasons for this site selection is the proximity to the substations. So higher voltage electricity takes less copper, as many of you know, and it's more efficient to transmit. So we bring 21,000 volt electricity into the top of the buildings. We actually run that down through the buildings, and we try and convert into our data center voltages as late in the process as possible. So that saves physical infrastructure, it saves copper, it also is much more efficient. We run most of the data center technology today at 208, so we run 3-phase power into the data centers, but we step it down as close to the racks as we can get it. I'm an electrical engineering guy by background, but it still makes me a little nervous to wander by those power distribution units, the humming, your hair stands up just a little bit. So, but I'm just kidding on that. So, extensive use of high efficiency motors, and we're also using variable frequency drives in fans and cooling systems. So, unlike a normal AC motor that's running at 100% capacity, we can actually feed variable frequency electricity to those drives, and we can run high efficiency AC motors, and we can run them at 30 or 40% utilization. And we have active monitoring systems that we can turn those systems up as the cooling demands require it, and we can turn them down when we're not using it. We maintain about 1,500 temperature sensors within the data center, and the building management systems looks at those temperature facilities and constantly monitors the speeds of those fan motors and the blowers and the cooling systems to exactly match the temperature profile that we're trying to build in the data center. If we take a rack of equipment and move it, the building automatically adjusts to the load and adds additional cooling into the data centers where we just move the equipment. This idea of virtual machines moving around the data centers and storage capacity moving around the data center actually automatically adjusts cooling and power distribution to accommodate the moves of those virtual machines and does it automatically without having to involve the system or the data center managers. We also maintain billing quality meters at the PDUs, energy monitoring in the back of every rack, and we're down to the point where we can monitor the exact energy consumption on a per plug basis really throughout the campus, but in particular in the data center. We had one of our PR people that came on an event with me, and she came in and said she had a heater under her desk, and one of those little infrared heaters under her desk to keep her feet warm during the winter. And she said, you know, the facilities people came by and took my heater away because they could tell that I was drawing more power than anybody else in the cubes around me. She goes, I was a little mad at first, but then I was so impressed.